Dr. Narasaiah can start now your talk. Start, please, Narsi. Share your screen.
Yes. Hello. Hello.
Yeah, go ahead, Narasaiah. We can see your screen.
Yeah. Whether it is screen visible, sir?
Yes, it's very good. Very good. Start.
Yeah. Yeah. Good morning to all. Myself, Dr. Narasaiah Palajonna, postdoctoral research from India. Yeah. Today I am going to, under the guidance of Professor Angelo Bostomada and Professor Pratap Kallu. Today I am going to present my work, that is the fabrication of iron oxide nanoparticle, ferrite nanoparticle 2D material. Yeah, this is the work we have done. This kind of material and iron material and 2D material and nanomaterial. In the case of part 1, we done iron oxide nanomaterial, zinc ferrite nanomaterial, so nickel ferrite nanomaterial, copper ferrite nanomaterials. And in the case of part 2, we done the 2D material, graphene oxide nanomaterial, reduced graphene oxide nanomaterial, and the graphitic carbon nitrates. So additional also we have worked on the tin oxide nanomaterial at different temperatures at 200 degrees and 500 degrees and 800 degrees. Yeah, synthesis of iron oxide nanomaterial through the chemical method and green method. Whereas we are looking for the chemical method, so require the high temperature, slow reaction process, and reducing is costly hazardous. Whereas we are looking for the iron oxide nanomaterial green method, so it's non-toxic, simple, and rapid, and low cost and high stability. So that reason we are looking for the synthesis of iron oxide nanomaterial through the green method. So that reason we are selected for the these are the eucalyptus leaf extract. The leaf was collected from the Tirupati forest area. So it is in India, Tirupati famous town and big famous temple in Tirupati. Yeah, this is the synthesis part of the iron oxide nanomaterial. So iron nitrate dissolved in 50 ml distilled water and added to dropwise the extract to the solution by using peristaltic pump. And stirring 70 degrees 600 rpm 3 hours. After we get the black color precipitation. And after that, after colloidal solution centrifuge 5000 rpm 30 minutes. And carefully pellets was collected and dried at hot air oven. So finally we will get the iron oxide nanometer. Whether synthesized material iron oxide material or not, we checked. So in the case of magnet, without magnet, we can see here. So without magnet, the material is down. In the case of with the magnet, you can see it is clearly attraction. It is like a flake type. So we confirm the synthesized material is a iron oxide material. Yeah. Further, we are confirmed the iron oxide for the XRD analysis. XRD pattern shows the crystalline nature of the material, and the XRD pattern shows the multidisciplinary peaks, which is corresponding to Miller indices. So, synthesized material will confirm the JCPDS, standard JCPDS. Whatever arises peaks, which is matches with the standard JCPDS. Look at here. This is the standard JCPDS. And average crystalline size calculated by Debye-Skinner equation. D equal to K lambda B cos theta. The average crystalline size is around 25 nanometers. It is 24.92 nanometers. Yeah, this is the synthesis of zinc ferrite nanoparticle, nickel ferrite nanoparticle, copper ferrite nanoparticle. 1:1 molar ratio of iron nitrates and zinc acetate dissolved in 100 ml distilled water. And after that, we are added to the plant extract. Then stir at 70 degrees 600 rpm 3 minutes. Formation of the brown color precipitation. Then centrifuge 5000 rpm 30 minutes. Dried at hot air to get the zinc ferrite nanomaterial. Yeah, this is further we are confirmed the XRD analysis give the crystalline nature of the material. So synthesized material we are confirmed the standard JCPDS number which is matches with whatever I just fixed, and the crystalline size was calculated by Debye-Skinner equation. D is equal to 19 nanometers. Yeah, this is the synthesis of nickel ferrite. Similar procedure we are followed. Protocol we are followed. We get the nickel ferrite nanomaterial. Yeah, this is the XRD analysis. Nickel ferrite nanomaterial matches with the standard JCPDS. Average crystalline size calculated Debye-Skinner D equal to 11 nanometer. Similar we are followed protocol synthesis of copper oxide nanoparticle. The 1:1 molar ratio of iron nitrate and copper sulfate, copper cellulose dissolved in the 100 ml distilled water. Then yeah, then we are similar protocol we are followed to get the copper oxide nanoparticle. But we can see here how it is. There is no matches with the standard JCPDS keras, standard JCPDS card number. So synthesizer material is we got a failure here. So what is the reason? What is the reason? Actually, we are identified that this once we are getting the yeah, look at here. Once we are getting the centrifuge, then wash with it several times. It is like a blue color. So that reason still it is blue color is there. So that reason we didn't get the proper XRD result. Yeah, this is the part 2 where synthesis of 2D material graphene oxide and reduced graphene as graphitic carbonated. Graphene is a material made of carbon atom which is bonded together to the hexagonal rings. Graphene is a so thin, it is considered two-dimensional, that is thickness of the at least one atomic layer. Graphene shows the extraordinary characteristics such as the strongest material in the world as well as the lightest, one of the lightest material. It is most conductive transparent. Graphene is the endless potential in the endless potential in the applications such as industries, batteries, capacitor, solar cell. Graphene is easily mixed with the in polymer other materials. So it is enhances the property of the material. That is like a tensile, electrical conductivity, and it is so used in many applications in this. And also we are making the one more material, 2D material, that is graphitic carbonate. It is similar type of 2D material like a GO. It is made of carbon and nitrogen. It is made of carbon and nitrogen. Graphene GC therefore used as a photocatalyst, autocatalyst, and energy storage material also. It is a simple method we can get without using any chemicals. We are making the 2D material. That is the advantage of GC34. This is the synthesis protocol of the graphene oxide. We can see how among all this method came on for synthesis of graphene oxide by modified Humber's method. Among all these steps came on for H2SO for really tough, came on for highly oxidizing it. It's highly oxidizing agent. So that reason it is the exothermic reactor. So that reason we are maintain the less than 20 degrees. And one more step is H2O, the hydrogen peroxide, is a free radical agent, highly reactive with the water molecule. So it will give the so that reason carefully and maintain this. So after that we are get the final graphene oxide. It is like a flake type. We can see here. After synthesis graphene oxide, we are characterize the UV XRD IR analysis. This is the protocol of synthesis of reduced graphene oxide and graphitic carbon. So in the case of we are reducing it with the 8 kilo plus steps. So we get the final product is very fine powder, reduced graphene oxide. So GC3 and 4 we prepare the by using urea without using any chemicals. So 5 grams urea dissolved in 10 ml of methanol, then stirred and stratosonicated and evaporated ethanol, and we get the precipitate and calcinate at 550 degrees 3 hours. So we get the final product. Yeah, this is the characteristic of graphene oxide, reduced graphene oxide, and graphitic carbon. From the FTIR analysis, identify the various components of the material and extract. The peak arousal is 3,300, which is 34 centimeter, which is corresponding to O stretching vibration, hydroxide stretching vibration. The peak at arousal 2,927 centimeter, which is corresponding to amine, so NS stretching vibration. We can see in GO and RGO. The peak at arousal is 1,724 centimeter, which is corresponding to carbonyl stretching. From XRD analysis, identify the crystalline of the material. We can confirm that there is no other peaks in the so GO and GC3 and 4. Yeah, this is the synthesis part of the. We have worked on the additional. So on the tin oxide metals. Tin chloride dissolved in 30 ml distilled water and by using a cotton peels extract. The extract was prepared by 3 grams of extract, 3 grams of powder dissolved in the 100 ml distilled water and kept in the hot plate with 70 degrees for 3 hours. We get the extract and after that filter with waterman filter paper. So then we are cooled at room temperature and then we are that synthesis of that is used for the synthesis of material. And after that we are tin chloride dissolved in 30 ml distilled water and proper addition of the extract by using peristil pump. Still at 603 watt. We get the milky white color precipitate and centrifuge 5,030 carefully pellets was collected and calcinated at a different temperature 200 degrees, 500 degrees and 18 degrees. This is the characterization of XRD analysis. It is shows the from 200 to the crystalline nature when increased, and we can see here in the 200 degrees and 800 degrees. So peaks as very sharp. So and also it will give the information the beta value. We can see how it is the peaks. Higher the beta value is a smaller size of the nanometer. This is the tabular column. This is the tabular column of the tinoxide nanometer. We can see look at here 200 degrees, the average crystalline size less than 5 nanometer. It is around 4.72 nanometers. The sample at 500 degrees is the average crystalline size is less than 10 nanometer we are making. So that is around 9.68 nanometer. Yeah, the material at 800 degrees, 800 degrees, the average crystalline size we are capturing less than 15 nanometers. It is around 14 nanometers. From the result, we are concluded from temperature increase from 200 to 800, the crystalline size was increased. Yeah, this is the TEM analysis, the transmission electron microscopy. It gives the information of the morphology of the material and the size of the material. We can see here and figure A and figure B. Particles are spherical nature. Average particle size is around less than 5 nanometer. It is AD means average diameter. AD means average diameter is 3.95, which is good agreement with the XRD result. Yeah, C represents the interplanar distance plane, planes. It is around 0.62 nanometer, which is resemble to the XRD result. D is represent for the set pattern of the material. E represents for the elemental analysis of the tinoxide nanomaterial. So F represents for the histogram of the particle size distribution. Yeah, this is the TEM electron microscope sample at 500 degrees. The particles are spherical nature. Average particles is average. That is nothing but the average diameter. So it is around less than 10 nanometer. It is 8.48 nanometer. Yeah, 8.48 nanometer. C represents the interplanar distance value. D it is around 0.26 nanometer, which is good agreement with the XRD result. D is the set pattern. D is the set pattern. E represents for the element analysis of tinoxide nanomaterial. There is no other impurities. Yeah, this is the TEM analysis of tinoxide nanometer at 800 degrees. It is shows the particles is clearly visible. So in the case of first sample, we cannot visible. Very small, so less than 5 nanometer. But in the case of, we can see third sample, particles are clear visible. A, B represents the different scale magnification. C represents the interplanar distance, which is around 0.26 nanometer, which is resemble to the XRD result. D represents for the set pattern of the polycrystalline. D represents for the set pattern. Selected area electron diffraction. So it is, we can see how a circular ring and a dotted spot. We can see first sample, there is no circular ring is there, but there is no dot spot, bright spot. We can see in second sample, the circular is there, but there is no dot spot. We can see in third sample, circular ring and bright spot. It is very good crystal. This is we can confirm the very good polycrystalline nature. E represents for the elemental analysis. F represents the histogram of the particle size. It is around 30 nanometers. Yeah, before this is the before going acknowledgement. So this additional I'll give very quickly, and the rest of thing one we didn't get the copper ferrite non-fluid, that one also I will do. That one also I will next presentation I will give. Yeah. Acknowledgement. I'm grateful thanks to funding agency. My sincere thanks to Professor Angelo Bostomona and Professor Pratap Pulli. He helped me a lot, and he is continuous encourage and supporting to me. And also thanks to Professor Luis Santos and Professor Dealing Jones and Professor Jolly Jones. My special thanks to the Anna Marina, head of the economy unit. I would like to thanks to postdoctoral student and doctoral student. I also thank to the master students. I thanks to the technicians. My sincere thanks to all the project group members. Yeah, my special thanks to the sponsoring agents. This is my house in my village. Yeah. Thank you. Yeah, thank you very much for all. And please suggest any suggestion and questions asked. Thank you very much for all.
Okay, thank you, Narasaiah.
Yeah.
Nice talk. Now, so the time of some questions. We are going to start with maybe Professor Reliang. Professor Reliang, do you have any question?
Yes, Luis, thanks. Thanks, Narasaiah. My question,
Yeah.
first question is, do you have a garden in your house?
Hello, sir.
Can you hear me? Do you have a garden in your house? We have not seen the garden. It has seen.
Cotton.
We've seen the gate. You have garden. That's very nice. So you look forward to seeing that in the future. Anyhow, for the iron oxide, the nanoparticles.
Cotton pills extract. Yeah.
Yeah. So, what do you use as the scale for making the iron oxide nanoparticles?
Yeah.
Could you show the process again? The for making.
Yeah. Iron oxide nanomaterial.
You start with the iron nitrate. You start with the iron nitrate salt.
Sir, I didn't get, sir, actually.
Yeah. Okay. So what's the starting material did you use for making the magnetite?
Iron nitrate, non-hydrate, so 9H2O.
Iron nitrate. But I'm thinking how we can use the scale from the oxidation of iron and steel for making the iron nanoparticles. Could we use the iron oxide particles to make the iron oxide nanoparticles?
Yeah, initially it is the iron +3 state is there. So after we are getting iron Fe3O4. So that means this oxidation stage in +2 state is there and +3 state is there. FeO and Fe2O3.
Sure, that's okay. So I mean we need to use the scale. You know the scale from the oxidation of the steel, like when rolling of steel, the surface oxidation will produce a lot of scales, like a layer of oxide, and that will fall down, and they call scales. And can we use those maybe to make the iron nitride? And then because that will make good use of the byproduct of steel making, and to make iron, make the magnetite. What is this called? Magnetite. Yeah, the magnetite nanoparticle, which is very useful.
Yeah. Okay. Yeah. Thank you, sir.
What's the magnetic property of this magnetite nanoparticle? Maybe Luis can also comment on this. The magnet is it?
Yeah, I will refer, sir. So I didn't check the magnet property still, but just we are confirmed whether it is magnetic or not with magnet. So sure, sir. Definitely, I will do that.
I'm thinking like how much quantity can you make this nanoparticle in large quantity?
Yeah, it is possible, sir.
Right, because if we can make large quantity, we can add these nanoparticles to like aluminum alloy or other alloys to make use of the magnetic properties, and also to react with another metal to make other nanoparticles for reinforcement of metals. Yeah, that's very good.
Definitely.
So what's the size range of these nanoparticles?
This 9 sizes we are calculated from the XRD. We get around 24 nanometers.
So you have not observed this one by using TM yet, because you show the TM images of other oxide nanoparticles. But we are more interested in this iron oxide nanoparticles, because these are the the part of the core of our project, because we want to make a good use of anything from the steel making industry.
Yeah, sure. Definitely, I will do sir. TEM analysis for this.
Okay. Oh, that's very good. Okay, thanks.
Yeah, thank you, sir.
I have to remember the pronunciation of your name. Yeah, thank you. Thanks, Luis. Yeah, that's my question. Yeah.
Okay, thank you very much, Professor de Lianza. Professor Ángel Bustamante, you have question, Ángel?
Sí, Mr. Narasaiah, it's possible to show for me the X-ray diffraction to oxide graphite? Because there is only two peaks. X-ray diffraction.
Yes.
The oxide graphene.
Yeah.
With
No,
the graphene.
another.
With the
There is
graphene.
some materials. Another. Is another.
The other XRD with the graphene, Narsi.
Sí, graphene or graphene.
Graphene.
Sí, show for me, please, because there is interesting two peaks, because graphene is two-dimensional structure. Yes, this is good. For instance, oxide graphene is the red. You have information about the power diffraction file to identify these two peaks. You have the information for this in literature scientific. There is another people to indicate these peaks. Si tiene el power diffraction file para la indexación de los picos, para ese, si él tiene la literatura.
Yeah, Narsi, I think
que nos pueda pasar.
Yes, Narsi, I think I can reply this. Profesor, sí, la literatura, sí, justamente usted ha publicado un paper acerca de eso, con nosotros, con Don Bugli, conmigo.
Es ¿cómo se llama? Es una estructura bidimensional, porque es igual sí, sucede en Raman, también tiene dos bandas.
Sí, le explico. La línea azul es de grafito. Tiene distancia interplanar más pequeña, ¿no? Distancias interplanares, porque es grafito. La línea roja es grafito, es oxígeno. Entonces, exacto, es solamente un pico, porque son bidimensionales. Entonces, la línea roja es del óxido de grafito. El pico está más a la izquierda. Sí, del óxido de grafito es la línea roja. Está más a la izquierda porque justamente se ha oxidado. Al oxidarse, los oxígenos entran entre los interlayers. Entonces, las distancias interplanares crecen, entonces el pico se va más hacia la izquierda. Entonces, eso de ahí hemos publicado.
Que era el de grafito. Okay.
Claro, hay un paper.
Another question in your Derrick diffraction in magnetite, there is a asymmetry line peak in the 511 peak. You show for me this X-ray diffraction, please. Magnetite. X-ray diffraction. See, no, yes, at the left, on the left, the 511 maybe to asymmetric is in this peak. It's possible to have some portion of magnetite, or it's only or there is a small magnetite. In 511, when you expand, maybe 2 is asymmetric. Those there is minimum 2 lines, 2 peaks. I don't know if there is a second phase.
Okay, le voy a explicar a Narsi. I will explain you, Narsi, what Professor Ángel Bustamante says. Professor Ángel Bustamante says that in the peak 511, that peak is very important in the XRD from magnetite. Why is very important? He says that it is important because that peak tell us you need to measure in very high resolution that peak. Why you need to measure in very high resolution, 0.001 step, for example, because that peak is deconvoluting in two peaks, or maybe it is more on the left or more on the right, it means that the crystal has some difference. It might be magnemite or might be magnetite. He has that experience saying that. That is why you need to measure in high resolution. However, that is what you are showing here. Is we don't. The answer, Professor Bustamante, I think that is for magnemite and magnetite. However, this is not magnemite, magnetite. This is thin iron 2 oxygen 4 nanoparticles, right?
Yeah.
Yeah. Profesor Bustamante, este de acá funciona en el magnetita y magnemita, pero el de acá, recordad que es ZNF2 o 4. ¿No?
Ah, sí, sí. Ah, ya, ya. Es circonio, o no, es ferrite, es una ferrite.
Yeah, sí. Okay.
Oh,
Okay.
sorry. Thank you very much.
No, don't worry.
Yeah.
Okay. Thank you very much. Any other question from the public? Quite quickly, any question for the public? Okay. Narasaiah, please remember that this is only your progress. You, in a couple of months, you are going to give another presentation with the progress of your paper, because every researcher in this group, every researcher should present, according to CONCYTEC, should present a paper at the end of this year. The progress of the paper, submitted paper much better, submitted or published paper, or at the end, if it's not submitted, not published yet, should be nearly finished the paper at the end of this year. So it is very important.
Definitely, sir.
Unfortunately, Professor Relian needs to leave in this moment because he is in another city, but he needs to come back to Shenyang. But we can say goodbye to Professor Relian, but we are going to continue this meeting. Okay, Professor Relian, no problema. There is no problem.
Yeah. Thanks, Luis. Yeah, Professor Angus. Yes, Marina. Anna. Marina. Thank you all, and Prata. Yeah, thanks for the effort. I'm sorry that I have to leave the meeting earlier because I have to catch the train. But it's good to see the progress made by anyway the from the work, and I look forward to the next meeting. Yeah, thanks. Okay, bye.